right, we're going to start. All right, so welcome to another AstroMcGill public outreach lecture. As you know, AstroMcGill is the public outreach arm of McGill, the McGill Space Institute, and it's a all-volunteer group of graduate students and postdocs and some undergrads from the McGill Space Institute. And one of our events are these monthly public outreach talks. And we also have other public events. For example, our monthly Astronomy on Tap, which will be happening next Tuesday. If you're interested, check out our the AstroMcGill Facebook, the AstroMcGill Twitter. We're advertising that. So Astronomy on Tap is also a couple of talks, but the talks are more shorter. They're like 20 minutes, and also the setting is more informal. We have those Astro on Tap events at McLean's Pub, so it's not like a classroom. So it's a little more fun in that sense. So before we begin, we have a couple of things. First, we have a raffle for the surveys. So we have some mugs. So our speaker, our speaker today brought some souvenirs from Arecibo Observatory in Puerto Rico. So we have some mugs and stuff for people who filled out the survey. So we're going to pull three names. So go for it.
The first number is 4904086. Who's got? I'll repeat the last four. 4086. No? Okay.
Next one.
The next number is 4135. Who's got? I heard something. No? 4135. Is that yours? Okay.
The first one? Okay, come on down. I think he has the first one.
Oh, he has the first one? Okay. Oh, you have the first one?
Come on down.
Yeah.
If you just stand over there, we'll get you. Cool. And we're going to pull one more.
The final Arecibo Raffle winner is number 4131. Nice.
All right. Awesome.
Perfect.
Cool. And we have one more thing to give away, which are a pair of planetarium tickets. And this is for people who took part in our Facebook tag a friend thing on the AstroMcGill Facebook. So do you have a name?
Okay, so the winner of the Facebook raffle is Erica Hornicker. Nice.
Nice. Awesome. Awesome. All right. Okay, cool. So for tonight's lecture, we have invited Dr. Flaviane Venditti. So Flaviane is from Brazil and got her bachelor's degree in physics from the University of Sao Paulo. And then afterwards, she got her master's and PhD in space engineering from Brazil's National Institute for Space Science. And then afterwards, she actually came to McGill. She was a postdoc here for a couple of years. And then now she moved on to Arecibo Observatory, where she's now a research scientist. And she's an expert on dynamics of asteroids and other near-Earth asteroids, near-Earth objects. And she'll talk about that, how to study that with Arecibo for us. So take it away.
Thank you and good night. I think that should do. Okay, so thanks everybody for coming. I'm gonna talk about our daily routine at the Arecibo Observatory, how we do observations using radar, and a little bit about the place the telescope is. So where is Arecibo Observatory? So it's located in Puerto Rico. So you are here, we are here. Puerto Rico is here, it's a little island. And it's a US territory. It's not a state, but it's a US territory. And the observatory is right here, close to the west side of Puerto Rico. So this defines pretty much life in Puerto Rico. So this is the window cave. It's called Cueva Ventana. It's really close to the observatory in Arecibo. And this is the most amazing water I've ever seen in the southwest of Puerto Rico. And this little guy, if you ever go to Puerto Rico, you might not see it, but you're definitely gonna hear it. It's really loud at night. It's called the Cookies, so they sing every night anywhere you are on the island. And you might have heard about the Arecibo Observatory in movies and TV shows. So this is my favorite movie, Contact, where Jodie Foster is an astronomer looking for extraterrestrial life in Arecibo. James Bond was fighting above the dish in GoldenEye. And this is one episode of X-Files. It was first episode of season 2. It was also filmed there. So where did it all start? So in 1958, William Gordon was a professor at Cornell University, and he began designing a radio telescope with the purpose of studying the ionosphere. So the official opening was November 1st of 1963. So why Puerto Rico? Why Arecibo? So this is how it looks like before the construction. So you can see it's already a natural sinkhole here. So it was already perfect to build the radio telescope there. So they started the constructions in December of 1960, and about 3 years after, they finalized the construction, and the operations started in November of the same year. So this is how it looks like now. This picture was actually taken 2 weeks ago, 1 or 2 weeks ago. So Arecibo Observatory is a 305-meter dish, and it's suspended. It's not touching the ground. So you can walk under the dish. There's a whole vegetation that grew there during these years. So there's some interesting kind of vegetations when you walk down there. And above, there's this suspended platform, which is just held by these 3 towers. It's really suspended. And it's 900 tons weight. So here's a picture of me up there. So I'm actually, so you to get up there, you go to on this catwalk. There's also a cable car, but there's this catwalk. So you go up, 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 up. It's a really fun walk. You look down and you can see through. You can see the dish under you, and it shakes. So you can go 5 to 6 people at a time. So the picture I'm here is taken right here. And the view up there is amazing. It's really pretty. It's my favorite place there. I asked for my office to be there, but they said no, so okay. So everybody thinks that the dish is a solid dish, because it looks like, but this is actually how it looks like. So there are 40,000 panels, 1 meter by 2 meters, and the whole dish, if you see under it, this is how it would look like. So in 1998, there was a major upgrade, which before there was this dome was not there. So we call it the Gregorian Dome, and inside this dome there are very, very important instruments. So inside here, there are 2 other reflectors. So the dish we call the primary reflector, and there are 2 other reflectors that send the signal to the receivers that are also here. We also have the klystron, which is this guy, and this is what powers radar. So who runs the observatory? So initially, when it was constructed, it was operated by Cornell University. And after that, National Science Foundation took over. And since April 1st of this year, National Science Foundation operates with University of Central Florida, which takes care of the scientists mainly, Young Enterprises, which takes care of the operational part, and UMAT, Universidad Metropolitana. My Spanish is not that good, but something like that. It's a metropolitan university, and they take care of the science outreach, visitor center. And since 2010, NASA fully supports the planetary radar department. So we have three departments. So planetary radar, where I work with. So we observe asteroids, comets, moon, and planets. Radio astronomy, so we observe several things. It's really known for pulsars. Space and atmospheric sciences, which studies the upper atmosphere, the ionosphere. So there are several radio telescopes around the globe, but radar facilities, there are actually two major ones. So it's Arecibo, where I work at in Puerto Rico, and Goldstone in California. So as a comparison, Arecibo has a 305-meter dish, and it's a fixed dish. But after the dome was added, actually it's a fixed dish, but it gave some flexibility because this dome can actually move up and down the platform. And Goldstone is a 70-meter dish, but it's steerable dish. So it actually can track objects for longer. So we have more precision, but they can track objects for longer. So we kind of complement each other. So the Arecibo radar system is the most active, powerful, and sensitive planetary radar facility in the world. There's nothing that comes close to what our radar system can do. And so we operate with 1 megawatt transmitter at S-band, and it started in 1980. So the first image ever taken of an asteroid was in 1989 of asteroid Castalia. This was before the upgrade, so the images were not that great. And the great thing about radar is that we can observe with rain, fog, day, night. Radar doesn't care. We can observe 24/7, which means we observe on holidays, weekends, so you're always there. So I take the night shift because I'm a night owl. So and it's really weird for me to observe during the day because I did optical in the past, so I was used to waiting for sunset, and there we can just, as long as the object is visible, we can observe it. And the Arecibo radar program, as I said, since October 2010, is fully supported by NASA, and the focus of the program are near-Earth asteroids. So each year we observe at least 600 hours, and which translates to about 100 near-Earth objects, and about 40 of them are newly discovered targets. This is the control room, part of the control room. It's a mess, yes, but it's fun. So all these cables, like every time we are observing, we have to change setups. We have to go there, change the cables, all of this, check the levels, adjust the levels. So it's very active. It's active observation. You're not just in front of your computer waiting. You actually have to do things while you're observing. So I mentioned that the focus of the program are near-Earth asteroids, but what are near-Earth asteroids? So the definition is the closest approach to the sun is less than 1.3 astronomical units. Astronomical unit is the distance from the Earth to the sun. So 1.3 times that distance, then it's considered a near-Earth object. So there are 4 types of near-Earth asteroids. These 2 are Earth crossing. This one has the orbiter exterior to the Earth's orbit, but interior to Mars. So Mars is like here. And Atira are fully within the orbit of the Earth. And among near-Earth asteroids are the potentially hazardous asteroids. The name is scary, but it doesn't mean they are something's gonna happen. They just have the potential for something to happen. So the official definition of potentially hazardous asteroid is the minimum orbit intersection distance of 0.05 astronomical units, and absolute magnitude, which is how bright the object would look like if you are from a distance from the Earth to the Sun, of 22 or less. So I'm going to translate this to simpler words. So PHAs are asteroids larger than 140 meters and that can get closer than about 19 lunar distances, 19 times the distance from the Earth to the Moon. another thing that we observe are NHATs. So NHATs are near-Earth object human spaceflight accessible targets study. So they are near-Earth asteroids that are well suited for a human round-trip mission to send an astronaut to it. So we also observe them. They are usually smaller targets, and they are also near-Earth asteroids. So radar observations, every year we send a proposal with the targets we want to observe. So we have the high priority targets, which are targets that will be, during that year, will be close enough and or big enough so we can get good images. And medium priority targets are objects that we can get lower resolution images, and also do radar astrometry, which is to refine the orbit. The survey nights are every new moon. We have the already scheduled survey nights about 2 or 3 days after new moon for newly discovered objects. So radar cannot discover targets because in order to send a signal, we need to know where the target is. So we have to wait for optical surveys or infrared to discover the target, and right after that, when you have the coordinates, we can observe. So why new moon? Because asteroids are tiny dots in the sky, so during full moon, it's harder to see these little dots in the sky. So every time after new moon, it's possible to discover more asteroids. So we have every month scheduled these days for survey nights without knowing if there will be a target or not visible, but we reserve those days during the year, yes. Also, we have urgent proposals. We are targets of interest that were not in schedule. For example, if you observe a newly discovered target that it turns out it's really interesting and we need to ask for more days, then we send urgent proposals. So how many hours do you observe each target? So usually you observe each asteroid for about 2.5 hours. And the target, because we are fixed dished and the position that we are, it has to be within the declination of from 0 to 38 degrees. So that's our limit of, so that we have to wait for the target to pass within this declination. For survey nights, we reserve 8 hours for newly discovered objects. So sometimes you can use this full 8 hours if there are enough new objects during those hours. Sometimes we don't use those 8 nights, but there are always about 8 hours reserved every new moon. So how does radar observation work? So as I said, radio astronomy is passive. You just wait for the light to get to you. So radar is active. So how it works is that we transmit a polarized wave with well-known characteristics. So here we transmit a wave, and we receive the echo from the target with 2 polarizations. So we send in 1 polarization, we receive in 2 polarizations, and we compare the transmitted signal. So we don't receive, we send a signal, but what we receive is much less than what it transmitted. And we control the transmitted signal, so any change is due to the target property. So how long does it take for that signal to come back? So for every target, we have what we call the round trip time. So it's the time that the signal takes to be transmitted until we receive the signal back. So around the telescope can track a celestial position for 2.6 hours. So we can see until Saturn. It doesn't mean that we are going to be able to observe any object until the orbit of Saturn. It has to be big enough for us to see it, but that is how far you can see, because the signal has to go and come back. So here you can see that we send a signal, but asteroids are rotating and they are not perfectly round shape. So part of the signal will come back first, the echo will come back first, and part of the signal will come back after. And that gives us the delayed Doppler images. So what do we measure with radar? So what we measure is the time delay, which is the distance, and we measure the Doppler frequency because the asteroid is moving and also it's spinning, so you have a Doppler shift. So with radar, this is actually what you see. This is a radar image that we see. So this is an example of a binary system. And if you are in space looking at this target, this is how you would see. So we don't have a 3D image with radar, but we can build with the radar image we get, we can build a 3D model. So here on the vertical axis, we have the delay, which increases downward, and the points at the bottom are closer to the observer. And the horizontal axis, we have the Doppler shift that increases to the right, and the points on the right are approaching the observer. So now I'm going to talk what is radar good for. So one of the things that radar is very good for is to refine orbits. So we can measure the position and the movement of celestial body with great precision. So we call it the radar astrometry. And this prevents newly discovered objects from being lost. Because sometimes you observe it optical, but then you end up losing the target because of the sometimes with optical you don't have like the perfect position of the target, and with radar we can adjust that. So this is an example of, it's the first thing we do every night, every day. It's called the CW, continuous wave. So here we have a Doppler frequency and the echo power. So we call this the signal to noise. So when you are trying to detect the target, we have a lot of noise. So the signal has to be strong enough so you can see that it's not noise and it's an actual signal. And then we move on to images or whatever we can do. So an example, this is a well-known target. So here, the Doppler frequency, you can see it's centered, but this newly discovered target, 2018 PL10, it actually has an offset of minus 34 Hertz. So then we enter a Doppler correction to help refine the orbit. So also, another thing that radar is good for is to detect orbit perturbation. There is one non-gravitational effect called Yarkovsky Effect, which is a solar radiation pressure effect. So it's a light push created when an asteroid absorbs sunlight and re-emits the energy as heat. So it depends on because asteroids are spinning, so while it's spinning, one side emits more energy, one side absorbs more, emits more. So the first, we knew in theory about this effect, but the first time it actually was measured was at Arecibo Observatory for asteroid Golevka, which this is the radar image and this is a 3D model. So it was measured during 12 years, and we saw that it drifted 15 kilometers in 12 years. So it doesn't sound like much, like 15 kilometers change, but imagine in 100 years, 200 years, 1,000 years. So an object that initially was not a threat can end up being in the future. So it's really important to detect any change in the orbit. Another thing that radar is great for is characterization. So radar can reveal size, shape, and spin of an asteroid. This is an example of asteroid 2014 JO25. They have weird names until they get a real name. And this, you can like clearly see that it's a contact binary. And it's estimated that 15% of the near-Earth objects are contact binaries. So, and this asteroid is a potentially hazardous asteroid, almost 900 meters long. And its closest approach in April of last year was 4.6 lunar distances. Another thing that radar is good for is to reveal surface properties, composition, and surface roughness. So we can measure the scattering properties. Remember I said we transmit a wave in one polarization and receive in two polarizations. So the polarization ratio can tell us the surface properties, sometimes the composition, if it's a smoother surface or not. So this is an asteroid, it's called Phaeton. It's the second largest asteroid, potentially hazardous asteroid known. And this asteroid is very important for us because it was the first target we observed last year after Hurricane Maria. I don't know if you know that it destroyed the island. And for at least 3 months we couldn't observe. This was the first image we got from an asteroid. So in this image, we could see an interesting feature. You can see here a dark spot, which could be a crater. And we also, before it was thought that it was the third largest potentially hazardous asteroid known, but then after this observation, we could see that it was actually 1 kilometer larger than it was predicted. So now it's the second largest potentially hazardous asteroid known. And just to mention, today is the anniversary of Hurricane Maria. Exactly today, last year, the Maria was hitting, made landfall. So because of that, usually observe with 2 or 3 people maximum. So for that, we were all there. It was like full crowded control room. And what radar is also good for is shape modeling. This is asteroid 1996 HW1. So here you have the radar image, and you can fit this model to build this 3D model. And this is very good for dynamic studies. It's very important for dynamic studies. Another thing that radar is good for is finding satellites. So asteroids, they have moons. I don't know if you can see, I hope you can see a little moon here. This is asteroid Atira, and it's little moon. Here it's easier to see. Asteroid 1998 QE2. This was observed in 2013. And sometimes we find more than 2. So here you have asteroid Florence. So this was the last target we observed last year before the hurricane. So Florence and Phaeton are very important for several reasons, but also for that. So we found out that Florence has 2 moons. And it's only the 3rd triple near-Earth asteroid known until now. And the size of Florence is 4.5 kilometers, and the moon size are about 200 meters each one. So the rotation period is 2.55 hours, and its closest approach was September 1st of last year, and it passed the distance of 18 lunar distances. Radar is also great for space missions. So nearly all missions to asteroids or comets are first characterized by radar. So especially missions to orbit and land, it's very important to know the environment you are. So the shape of the asteroid, the rotation period, the composition, all of these are important before you send a spacecraft to it. And many times, radar images can be equivalent to a spacecraft flyby for way, way, way cheaper. So this is asteroid Tethys. This is a radar model during its closest approach in 2003. And in 2013, spacecraft, I don't know how to pronounce this, it's Chinese, Chenji, not sure. There was this spacecraft visited Tethys and took this picture. So in this case, you can see how similar it is, the radar image that it did from ground, and a spacecraft that costs a lot of money to send, which is really cool, but sometimes you can save money by characterizing from here using radar. So some of the asteroid and comet missions supported by radar, these are just some of them. So some already happened, some are ongoing, and some are planned. So OSIRIS-REx is actually gonna arrive at asteroid Bennu next month, and this one I'm gonna talk later. Destiny Plus, it's a Japanese space agency, and it's going to Phaeton. I think it's planned for 2022. And Psyche, it's a mission to a metal asteroid, so it will be the first mission sent to a metallic asteroid. Our latest radar discovery was asteroid 2017 YE5. If someone follows asteroid news, you might know what I'm talking about. So this little dot moving here, hope you can see, was discovered last December by a sky survey, and in June of this year, it was visible for us, for radar. And when we were observing, we actually had a big surprise that instead of a little dot, we found this. So we actually found two, and they are equal mass binaries, which is really rare to find. So This is the only fourth equal mass binary near-Earth asteroid known, and this was the best image ever obtained of an equal mass binary until now. So with these images, you could see that each asteroid is about 900 meters, and they rotate around each other facing the same side, which we call it tidally locked. And also with the images and the analysis we have, they also show that they might have different compositions or surface roughness. And the closest approach was, it passed 16 lunar distances from us. This is a radar image of Jupiter. Yeah, that's what you would see. Remember I said that radar can see, it doesn't matter if there's fog, rain, the atmosphere, so Jupiter is a gas giant, so you actually don't see Jupiter with radar. And Saturn, you also don't see Saturn, but this is from 20 years ago. You can actually see the rings, but you don't see Saturn too. And this is my favorite Arecibo image of a planet, Mars and Venus, I will show. So meet Venus and Mars. They are space cat brothers. They were born there and they are still living there. We feed them every day. But now I'm going to show you a real image of Venus. It's not that cute, but this is a radar image of Venus, and it was the first image of the surface of Venus, because with optical you actually see the atmosphere, and radar can pass through the atmosphere. So this was the first image of the surface of Venus. And this was observed with Arecibo in Green Bank telescope in West Virginia. So Arecibo sent a signal and Green Bank received. So a history of the radar detection of near-Earth asteroids until now. So here is Goldstone and Arecibo together. So radar program started in 1980. So you can see that like until 2010, you would observe maximum of 20 asteroids every year. And since NASA began to fully fund the planetary radar program, it increased to more than 100 per year. So what do we know so far about near-Earth asteroids? Until 2 days ago, we might have new numbers, but it's known 18,805 near-Earth asteroids, and 781 of them were observed by radar. It's estimated that about 15% of all near-Earth asteroids are contact binaries, which one of the reasons that is thought for them to exist are collisions, so how they form, it's one of the theories. And we think another 15% are real binaries. So with radar we found 61 of them. We know only 4 equal mass binaries and 3 triple near-Earth asteroids. So it doesn't mean there are not more, but it's hard to see. It's hard to see the primary asteroid, imagine the moon, so you can actually just see with radar, or if you send a spacecraft and then you find a moon when the spacecraft is near the asteroid. So here you have in red the number of asteroids larger than 1 kilometer. You have in orange asteroids larger than 140 meters, and the rest in blue. So it is almost 20,000. So are we in danger? Important question. So not yet, not anytime soon. Not yet, no, sorry. I shouldn't say that. Not anytime soon. So 95% of the potentially hazardous asteroids larger than 1 kilometer are known. More than 8,000 near-Earth asteroids larger than 140 meters are known. And the goal is to discover 90% of near-Earth asteroids down to 100 meters by 2020. And every week with asteroid surveys, we discover about 40 new near-Earth asteroids. So why is radar important for planetary defense? So asteroid impact is actually the only natural disaster that we can do something about it. We can't stop hurricanes, tornadoes, earthquakes, but asteroids, we actually can do something about it if we know in advance. So one of the things the radar is good for is to refine orbit. As I said, an example I'm going to give is, you might have heard about Asteroid Apophis. It's a 325-meter asteroid. So when it was discovered in 2004, there was a lot of talking because it was thought that it was going to collide with Earth in 2029. And after it was observed by radar in 2005 and 2006, that possibility, it ruled out the possibility of collision. And so what you know now is that Apophis is going to fly by Earth on April 13th of 2029 at a distance of 0.1 lunar distances, which is about 6 Earth radius. It is close, but it's just close enough to get good images. It's not a threat. And also, we can detect very small changes in the orbit. As I said, for example, the Yarkovsky Effect. So it's important to know the orbit of the asteroid, but it's important to know what is affecting this orbit too, because it might change in the future. It's also fundamental for characterization. So if we need to send an asteroid deflection mission, we have to know the characteristics of the asteroid, the mass, the rotation, the composition, in order to choose the right method. So, asteroid deflection, what are the steps in case we ever need? So, first of all, you need to find the asteroid. So this is done by asteroid surveys, mainly optical infrared. Second, we have to track the asteroid. So this we do by radar, using radar too. And third one, characterize. So this is where radar is really crucial because there is no other way from the Earth to characterize, to know the shape, to know the spin. Sometimes we can know some things with light curve, but radar is really good for characterizing. And finally, choose a deflection method. So I'm going to talk briefly about some of the popular ones. Asteroid deflection methods. So for a short warning time, when you don't have much time to do anything, what you can do, nuclear explosives, Armageddon style, with hopefully not Bruce Willis, and kinetic impact, which is to throw an object on the asteroid and try to move it a little bit. So for now, I'm going to talk about some popular long warning time asteroid deflection methods. So you can place a solar sail on the asteroid, so it will to help evaporate the surface layers, and you will give a boost, so slowly push the asteroid away. Gravity tractor, which is to place a bunch of spacecrafts around. You know, mass attracts mass, so if you place a bunch of things around the asteroid, you could give a little gravitational pull and slowly move the asteroid. So you can use the Yarkovsky effect. So you can increase or decrease by changing how much heat an asteroid radiates by making it lighter or darker. Literally painting one side of the asteroid could do something. But solar radiation pressure affects more smaller asteroids, so hundreds of meters, maximum 100 meters, something like that. So then the solar radiation pressure would have more effect. Any asteroid deflection ever tested until now? Actually, no, but there is one planned. So it's called AIDA-DART, and AIDA stands for Asteroid Impact and Deflection Assessment Study. And DART stands for Double Asteroid Redirection Test. So they are part of the same concept. So this one is from the European Space Agency, and DART is from NASA, and there are many other institutions working together. So an overview of this mission is, so in 2003, we could observe this asteroid called Didymos, and then we saw that it actually has a moon. This is a radar image we took from at Arecibo Observatory, and the idea is actually to crash a spacecraft on the moon to test the kinetic impact. So the primary is about 800 meters, and the moon is about 150 meters. So the idea is to crash a spacecraft on the moon and watch how the orbit changes. So the last closest approach was 2003, and the next closest approach will be October 2022. So that is when it's scheduled for the impact date, because then we could observe, it would be flying by. It's a close approach here, so we can observe with radar, optical, and we can measure that change in the orbit of the moon and the whole system, actually, how it affects the whole system. This is how they plan to do it, the concept. So it's pretty much sending a spacecraft and just crashing on the moon. So it's you got to start somewhere, right? So this is like, if you have a very short time, what you can do, because many of the methods, it takes a while. It changes slowly. For example, using solar radiation pressure or gravity, you need time for that to happen. But if you don't have time, there's not a lot you can do. So some of the discoveries at the Arecibo Observatory, and this, I'm going to mention just a few of them, and from all departments. So until 1965, it was thought that the rotation rate of Mercury was 88 days. And with radar, it actually found out it's 59 days. Also, the precise determination of the astronomical unit. Also at Arecibo, it was discovered the first binary pulsar, which led to the Nobel Prize in Physics. The first image of the surface of Venus that I showed, until then we could just see the upper atmosphere. The first exoplanet ever discovered orbiting a pulsar, actually first exoplanet discovered at all, and it was orbiting a pulsar. The first binary system, near-Earth asteroid binary system, was asteroid 2000 DP107. The radar refinement of the orbit of Apophis, that then we could realize, no, it's not going to collide. It's going to pass close, but it's not going to collide with Earth in 2029. The first measurement of Yarkovsky Effect, which is a solar radiation pressure effect. Discovery of the first triple asteroid system, 2001 SN263. So I said we only know 3, so that was the first one discovered. And 2016, the first repeating fast radio bursts. These are some of the discoveries there. And if you want to know more about radar and asteroids, you go to these websites. They have a lot of nice information. And I'll leave you with this. This is a phrase from William Gordon, which is the person who came up with the idea of Arecibo Observatory. And thank you. Oh. You mean active, you mean how radar works? It's active because we are the one who sends the signal and we receive the echo that we send. Yes, all the images I showed. All this, I mean, yeah. No. So the signal is actually a microwave microwave that is sent signal, and it's not really the sunlight that we are detecting. It's not like optical. What we are detecting is how it's moving, like the distance it is, and how fast it's moving and spinning. And then we transform that after a lot of things happen inside all those cables that I showed you. Like, then we transform that into an image. It's just 'cause it's a 2D image, it's not a 3D image, so you have a different impression. So when you are first seeing a radar image, it actually tricks your brain because you tend to think 3D. I mean, for me, it takes a while to understand that we are seeing is not exactly if you're seeing in front of you. The impression you have is not exactly if you are seeing the asteroid. You have to transform that image into a 3D so it actually is what your brain is thinking it is. So. Yeah, so we have other things around, but it's very, like, we send exactly to that position. So actually we have noise, but we are sending exactly pointing at that little spot. So you actually, if you have when you see a detection and you see the strong signal and you point it exactly to that, you know the characteristics of asteroids in general. So yeah, it's almost 19,000. Maybe, but maybe today it became 19,000. 81, yes. So. So radar, as I said, it doesn't discover asteroids. So we observed 781 on radar because they were visible for us. They were available for us. They were big enough and close enough for us to detect them. Because sometimes we try to detect, it's visible, but then the signal is not so strong, so we don't have a detection. So it's 781 because those are the ones since the program started, they were visible for us. But you mean to discover asteroids? So infrared space telescopes can also detect the heat from the asteroid, but it has to be a space telescope because you cannot have other thermal perturbations to detect it. From Earth is mainly optical, and you have infrared space telescopes that can detect too. So it's easier to detect that asteroid. So he means this one, right? So this one was, I think, it was about 30 meters, if I remember correctly, something like that. It was way less than 100 meters. So the problem is that it's easier to find asteroids larger than 100 meters usually. So it's getting better. You're being able with new instrument, new service to detect smaller asteroids, but sometimes you can't detect. And also with optical, if the sunlight, it depends on the position it's passing, sometimes the sunlight will, you won't be able to detect because of the sunlight. It has to be bright enough, for example, new moon, this kind of things, because it depends if it's coming or going towards the sun, the sunlight will play a role in it and you can't see it, especially when it's too small. 30 meters, 50 meters, it's very small to see space. So.
Can you see the radar image live, or does it require a lot of photograph?
No, so we see live. So while you're observing, we have to process it. So in optical, the data reduction, I think, still done after. But yeah, you see, like for example, what we don't sit there and wait for it to appear, but oops, come back. Okay. So we have to set up the cables, the mode that we want to observe, the right setup, and we receive. So how it works is during radar observations, what you have, it's like receive, transmit, transmit, receive, transmit, receive, and after some scans, we process that image. There's like a little manual that we follow to process the image, and then we can open the image with those scans we observed. So sometimes if you're observing for 2 hours, one asteroid, in the first 30 minutes we can try to process those scans. Scans is like each transmit, receive, and then we still don't see anything. But after 2 hours, you add all those scans, and then you can see. So while you're observing, we see it, because sometimes we have to change setups in case we are not seeing, and we see, oh, it's not good resolution enough. We have to change to another mode. We have different kind of setups for image, so we can see it while you're observing. It doesn't automatically pop up on your screen. Like you process it, and then you have it. So that is actually not my area. This is radio astronomy. So I prefer not to answer that, and it was because of a pulsar. So probably because pulsars are really like precise, the timing. So probably because they detected some anomaly in that time. But I'm not going to say that for sure, because it's not my area, radio astronomy. So I'm in the other department. So I prefer not to say how it was done. So. Yeah, if anybody here does radio astronomy, and because radar and radio astronomy and radar, planetary radar, are totally different things. We use the same equipment, but how it's done is completely different.